Okay, these are some problems from section 9.3, and we want to find the Taylor polynomial of order 4 for the function, and then use it to approximate the value of the function at x equals 0.2. All right, so my function, the first one, number 1, the function was f of x equals e to the negative 2x, and all we did was take the 4 derivatives, so we could do the fourth order Taylor polynomial. So here we go. F of x equals e to the 2x. The first derivative will be just e to the 2x times, e to the negative 2x. And the first derivative will be the e to the negative 2x times the derivative of negative 2x, which is negative 2, so I just multiply by negative 2. And remember, the derivative of e to the u is e to the u du, so the derivative of my u is always going to be negative 2, so I just keep the e to the negative 2x, and I just keep multiplying by negative 2. That gives me 4. By negative 2, that gives me negative 8. By negative 2, that gives me 16. So those are your first 4 derivatives and the 0 degree. And then I just evaluated that at 0 because this is going to be the function evaluated at x equals 0. So we just put 0 in for our derivatives, 1. So e to the 0 is 1, so this just becomes 1. Negative 2 times 1, 4 times 1, negative 8 times 1, and 16 times 1. And then I do this, and it's good just to do this for practice so you really know the Taylor expansion. So if you see it on the AP exam, you don't have to think twice. You know it really well. Just write it out every time. And, you know, some of you may think that's a waste of time, but it's a good way to remember the formula. So fourth order polynomial, 0, f of 0, x to the 0, 0 factorial, 1, 1, 1, 2, 2, 2, 3, 3, 3, 4, 4, 4. And, you know, if you write it out, you won't have any trouble. And these are f equals 0, f of 0, I should say. And these were the numbers I had from up here. 1, negative 2, 4, negative 8, 16. And these are the numbers I got from the Taylor expansion. And we simplified x to the 0, 0 factorial is 1, and that was 1. And x to the first over 1, x squared over 2, 2 factorial, 3 factorial is 6, 4 factorial is 24. And then we just simplified. I used one more step to simplify it, which was just 2 and a 4. That reduced to be 4/3, and that reduced to be 2/3. And then I just put it in my calculator. I just put this in my calculator and used var y vars, and I evaluated at 0.2. And this is what I got. Let's get this just a little bit higher, and you can see there. So again, you just put this into your calculator, evaluate it, and the f of 2, the actual value, which is approximated by the polynomial, is this, and that's your approximation. Okay? So just some more practice with Taylor expansions. Actually, in this case, it's Maclaurin's because it's about 0. So these are all Maclaurin expansions. Number 2. Let's take a look at number 2. A little bit more complicated. Cosine of pi over 2 times x. So again, the derivative of the cosine or the sine is going to be either the derivative of the cosine is negative sine, the cosine of the sine is the cosine, and it's always going to be du, so I'm going to multiply by pi over 2, because that's the derivative of my angle. So the cosine of u du, the derivative of du will be pi over 2. The derivative of the cosine is negative sine, and I multiply by the du. Cosine, the derivative of sine is the cosine, and I multiply by pi over 2. So pi over 2 times pi over 2 is pi squared over 4. Now again, I'm going to just start with my function. I'm going to take my 4 derivatives, just like in the last problem. We do that in the first 5 problems. The same thing, same setup. Well, almost. We can get away with it in a couple of them, or at least one of them. Anyway, so let's take a look at this. So the derivative of the sine is the cosine, so sine stay the same. Well, again, I multiply by pi over 2. The derivative of the cosine is negative sine, so I got a negative times a negative is a positive. So, and I multiply this by pi over 2, and I get pi cubed over 8. And the derivative of the sine is cosine, and I multiply this by pi over 2, and I get pi to the 4th over 16. So those are your first 4 derivatives and your function. And then we just evaluate those out at 0. Cosine of 0 is 1, so this is just 1. Sine of 0 is 0, so that goes away. Cosine of 0 again is 1, but I've got negative pi squared over 4 times 1. Sine of 0 is 0, so that's going to go away. And then the cosine of 0 is 1, and this is going to be positive. So again, I wrote down my general form. I just do that for the practice, and I would highly recommend it. And then P sub 4, this is f of 0 was 1, f prime of 0 was 0, so that first degree term disappeared. Okay, and then this was negative pi squared over 4, so that's my second degree term. Remember, the first degree term disappeared because of the 0, and so does the third degree term. All right, but it's still order 4 because I'm taking it out to the fourth derivative. I'm evaluating at the fourth derivative, even if some of the derivatives zero out. So this is still of order 4. Goes to the fourth degree, but I only have 3 terms in this case, not the normal 5, because 2 zeroed out. And again, this fourth was pi to the fourth over 4. I'm sorry, this is pi to the fourth over 4 times x to the fourth over 4 factorial. So pi to the fourth over 16, pardon me. All times x to the fourth over 4 factorial 24. So these are my 3 terms. Okay? So we substituted this, and this. Okay? And then I simplified it. 2 times 4 is 8. And then 24 times 16 is 384. And I got my pi squared, x squared, pi to the fourth, x to the fourth. Okay? And then again, we want to evaluate that, or we want to use that to approximate the value of the function, so we just put 0.2 in there. And you can put it in your calculator. That's what I put in my calculator, put 0.2 in, and I came up with 0.9511. So f of 0.2 is approximately the Taylor polynomial evaluated at 0.2, and that gives me the approximation. Okay? And you can put that in your calculator and find out. Now, this is something we could calculate. We could take 0.2. We could do this algebraically. That's the point. We could do this algebraically. All right? We'll find out a little bit later how accurate or a good bound on that error is. That's what we're talking about, the error bound. To see how close we would have to be, we'd have to be within a certain error. But you couldn't do the cosine of pi over 2x at 0.2, or you couldn't do the cosine of, that would be 0.2 pi over 2. I guess that would be, probably reduce that to be pi over 10 or something like that. You couldn't get that out without a calculator or without trig tables, and here you could calculate this out. So you could do this numerically, that's all I'm saying. So this could be done, because you know what pi is, you have an approximation for pi, so you can approximate that out. Okay? So that could be done. So that's the point. We have a way of evaluating these transcendental functions algebraically. So we could work this out with enough time and enough paper. Okay, we could do this. We couldn't do it this the other way. Okay, and you could check that with your calculator and see how close you came. And that would be 0.2 pi over 2. And if you multiply the top and the bottom by 10, you would have 2 pi over 20. Yeah, pi over 10. I think that would be the same thing as pi over 10. Okay? Hope this helps.